Welcome back to machine learning. This video is going to cover imitation learning. First, we're going to talk about what imitation learning is. We're going to talk about an algorithm for imitation learning using classification, and then we're going to talk about the dagger algorithm. First, let's talk about imitation learning and what it is. We've covered a lot of classification problems in this class, focusing on one sample and one decision. However, there are many problems that involve a temporal or time component. These are called sequential decision-making problems. In this lecture, we're going to consider the problem of training a self-driving car. We want the car to mimic an expert driver. Another word for this is to imitate. The expert is sometimes called an oracle or something that knows the right answer and can be queried at any time step. Imitation learning is also known as learning by demonstration. We're trying to create a learning framework that, for lack of a better word, mimics the way that humans learn. Children mimic or imitate their parents and learn how to do things. Using a self-driving car as our example, we want to imitate an expert driver. Here's the problem setup. At each time point, t equals 1 to capital T, the car receives some sort of sensor information, xt, like radar sensors, video information, GPS, any of these things. This is the input, or the sample, and then the car must take an action, at. That's going to be the output. What can the action be? Well, it could be different steering directions as well as speed changes, increasing, decreasing, or maintaining. The car then suffers from a loss, LT. This can be small or zero if the car is driving well, or large if something goes wrong, like there's a crash. The car must again predict some action AT plus 1, receiving loss AT, LT plus 1, and so on. This is an iterative process. The goal is to learn a function f that maps inputs to outputs, that is, sensor information xt to action at, with a minimal loss lt. Because imitation learning is so closely related to reinforcement learning, this function is sometimes referred to as a policy. How do we measure the success of a policy? Well, we need to run the policy and see how much total loss is suffered. Suppose we have these trajectories, tau, that consist of an input, an action, and a loss for each time step, where the action taken at time t is equal to the function or the policy of the input. The goal of f is to minimize the expected loss. Why is it the expected loss and not just the total loss? Well, because the randomness in the world. The ever-changing world cannot be accounted for in absolutes. There's a lot of things going on here, but we don't want to get confused by it, okay? All we're trying to do is minimize the loss. This E just says expected. Tau tilde F just means that these trajectories are sampled from a policy, and then we just sum over all time steps. Now let's move on to actually doing imitation learning using classification. One really simple approach to imitation learning is to treat it just like a bunch of classification problems. We can assume we have access to a set of training trajectories taken by an expert. So we have a bunch of examples of an expert driving. So we're basically training a multi-class classification model to take an observation and predict an action based on many trajectories provided by an expert. This is doable if the action space is discrete. That means if we just have a set of possible actions that we can output, then we can learn a multi-class classification model. The algorithm is pretty unstable though. Let's talk about the algorithms first before we get into that. This is the supervised imitation training algorithm. All it's doing is collecting all observations. So it's just collecting data from an expert and putting it into this little thing called D, which is going to be our data set. And then this line just says train a multi-class classifier. You can use anything that we've done before. We can use a bunch of perceptrons. We can use an SVM that's multi-class or anything. Now, how do we actually test? Well, we run through time steps, right? And we take our current observation and then we use the policy that we trained and predict an action. And then we take that action, we observe a loss, and then because of that action, we have a new observation and we move on from there. How well does this algorithm work? Well, it depends on the expert. If you're imitating a crappy driver, then you will learn how to drive poorly. It's also unrealistic to expect this algorithm to improve on an expert's behavior since it's learning directly to mimic it without knowing what other options there are. This algorithm is pretty unstable since you have to have a lot of trajectories to learn possible actions based on all possible inputs. The biggest issue here is compounding error. If the predictions are a little off a few times in a row and the car ends up facing a wall and the expert has never seen a wall, then all sorts of bad things can happen. Moving on to the dagger algorithm, which is a little bit more reasonable. The dagger algorithm stands for dataset aggregation. This allows us to train a policy that can deal with all possible situations, even if the expert has not encountered it before. What we need to do is to train a policy, F, to do well on configuration it encounters, not just the ones an expert encounters. We're going to use an iterative approach to solve this problem. We're going to start with some policy F. We're going to run F and then see what configurations it visits. And then we're going to train a new F to do well in those configurations. And then we're going to repeat. Basically, we first let a human expert drive a car for a while. And we learn an initial policy F0 by running standard supervised imitation learning, just like we just learned, on the trajectories from the expert. Then we put the human expert in the car. So now we have a policy that we've trained using just the classification algorithm that we just talked about. We put the expert in the car and we record their actions, but we don't listen to them. So here's the car. Okay, the car moves and the expert says, okay, well, if I were driving, I would have kind of turned a little bit. And the car says, okay, thanks, I've noted that. And then continues. And then asks the expert again to make a correction. So now the corrections are getting more aggressive because the car is getting further and further away. And the car again just says, okay, thanks, I noted that. And again, and at this point, the action from the expert says, I would turn a little bit and also stop. Because at this point, this isn't recoverable. And the car says, okay, I noted it, and then crashes. So it drives according to the learned policy, noting the actions that the expert would take. And we now have training data for how to recover from errors. So we train a new policy, F1. F1 is trained on the union of the two sets of data we have. That is, from the original policy that we trained, and then this new set of data with expert corrections. We repeat this process many times to produce a list of all policies learned. Now at the end, we have many policies. Which one should we use? An obvious choice would be the final one. However, dagger can be somewhat unstable in practice, and policies don't always improve with each iteration. The best option is to test all policies on some held out validation data to see which one performs best on unseen data and use that one. Here's the actual dagger algorithm. Basically, we run an expert n times to get our training data, right? Our trajectories. We collect all those into a data set and we train an initial policy using a multi-class classifier. Then we run this policy producing trajectories, and then we take input from an expert and then just continue. And then all we do is we train a new policy on the union of all the data that we've collected. And we return all of the policies that we've learned, okay? And then we have to make a choice as to which policy to save or to use. So we could use it like an ensemble and have a bunch of voting, or we could choose the most recent one, or we can use the validation data to help us choose one. It seems obvious that we can't use dagger as it currently exists in the real world because we can't just let a car drive an expert into a wall. So we actually use expensive algorithms as experts. An example would be game playing. We can play a game like chess in simulation to explicitly compute a semi-optimal expert behavior with brute force search. But this search is too expensive to play in real time. So we use a simulation of the expensive algorithm as the expert to train an imitator. This video covers what imitation learning is, how to do it via classification, and a better algorithm called dagger. The next topic is reinforcement learning, which builds on imitation learning and is more general purpose.